Hello. This is a presentation on causality in systems thinking, especially, but not only, in causal loop diagrams. Where we're heading is to build up a model of causality in causal loop diagrams, but we're some distance from that, and we'll get to that at the end. The presentation is in three parts, starting with a discussion of graphs. And this is only scratching the surface of graph theory. For more, I do recommend Robin Wilson's work on this. The basis of graph theory is that when we draw a diagram like that, it's composed of vertices connected by edges. Every edge connects two vertices. A causal loop diagram is usually a connected, directed, cyclic graph. What do we mean by that? Connected, every vertex is connected to at least one other, and thereby indirectly to all the others. Directed means that the edges have a direction, conventionally shown as an arrow. Cyclic means that somewhere in the diagram there is a cycle that we can walk around, and starting from one place and returning to the same place. This is an aside I'm going to skip. In terms of graph theory, a tree has only one root between the vertices, as you will find in an organization hierarchy, for example. So the most common kind of structure we're interested in enterprise architecture documentation are hierarchies. And in fact, we have three kinds of documentation in enterprise architecture: catalogs, matrices, and diagrams, and all three of those can be viewed in terms of a graph. But our focus is on diagrams in particular. And we want to build a meta model. So here's an example of a diagram. The meta model describes the contents of the diagram. The two concepts are vertex and edge. Every edge connects two vertices, one at one end, one at the other end. Every vertex has connected to many edges. We'll see that meta model again later. So part two on two kinds of diagram. In fact, there are many kinds of diagram. The diagrams we draw, we don't talk about vertices and edges. We talk about parts and relationships, or stocks and interactions. We have many varieties of diagram with many differently named concepts in them. If a system is a collection of parts that interact in a whole, and that's a very naive definition, but good enough for here, a system can be shown in terms of the parts it contains and the relationships between them. We're very interested here in state change over time. So here, a system in state one moves to state two, moves to state three, and as it does so, the parts change state. There is the micro state of each part and the macro state of the system as a whole. There's a second kind of change, which is changing the system itself, changing the kinds of parts and the kinds of relationship in the system, which is out of scope here. Talking about parts that interact in a whole, we have many ways of talking about parts, many ways to talk about relationships, many ways to talk about a whole, and many ways we can represent these things in diagrams. Of the many diagram types, we're focused here on two: entity relationship diagram and causal loop diagram. An entity relationship diagram shows relationships between things. The things are called entities. This entity is connected. One of those is connected to many of those. The symbol is a one-to-many relationship, which is what we're focused on here in this presentation. The causal loop diagram shows the effect of one stock on another stock. Stock, also population or resource. We'll look at that in more detail in a minute. First, the entity relationship diagram. What are the entities? Well, an entity can be a role, an event, a state, a process, or even a relationship. So here, an assignment is in effect an entity that represents a relationship between one employee and one project. What is the entity relationship diagram? It's a representation of relationships that we can express in natural language, in predicate statements of the kind subject is related to object. So here, one employee is related to many assignments, is given many assignments, and one assignment is carried out by one employee. Causal flows are also representable as predicate statements. A source has an effect on a target or causes a change to a target. Any kinds of thing can be a source and a target here. The effect is a change to the target, perhaps quantitative, change of dress or change hair color, but our interest here is more in quantitative change. How to represent causality. I'm going to talk through the first 3 or 4 diagram types here, ranging from informal to formal. First, very informal concept graphs. For example, pressure to lower prices causes us to reduce the number of staff and rely more on IT for communicating with customers, which, as we all know, leads to worse customer service. So there's a cause to the left and an effect to the right. Why do we draw diagrams like this? To tell a story, make a point, like I just did, to show the complexity of a situation, or to help build an animatable system dynamic model that we can use for forecasting outcomes. This diagram is a more quantitative influence diagram, is the term I'm using here. It's not quite a causal loop diagram, not quite as formal as that. It's showing an increasing a source variable likely causes an increase or decrease in the target. So increasing road miles cycled per person likely increases fallen collision deaths and pollution inhaled, but it also increases average fitness. And these 3 effects are in turn causes which have different effects on average lifespan, which makes it difficult to forecast. Another influence diagram here is just designed to show the complexity of defining a policy to do with energy, climate, and land use, because all 3 interact. You can dwell on that at your leisure. Moving to a more formal causal loop diagram, the convention is to label the flow plus or minus, or same or opposite. And we'll see what that means on the next slide. A positive flow shows source and target change in the same direction. So an increase causes an increase, and a reduction causes a reduction. A negative flow shows change in opposite direction. So an increase causes a reduction, or a reduction causes an increase. And I've used the famous predator-prey example to illustrate this. And we can connect those 2 causal flows in a feedback loop. And it's true that people do causal loop diagrams looking for such loops, but it's actually a rule that you must have loops in a diagram. The systems of interest here, given that there are open and closed systems, designed and natural systems, inorganic and organic, linear and nonlinear, people usually draw a causal loop diagram to model a system of interacting variables that is closed and nonlinear, but they can represent linear systems, and I've shown one here. We have a cause-only source and an affected-only target, and the process runs from one to the other. If you try to animate this process, it would run to a completion. If you wanted to animate the effect of changes over time to the cause-only source, you could either reset the variable and rerun the process, or connect it to itself by a loop that perhaps continually increased it. Here's another example of a diagram without a causal loop diagram without loops in it. What does flow mean? Generally, flows in diagram shows something that happens over time. In a process flow chart, we're showing activities, and the arrow connects the earlier activity to the next activity. it shows a transition from activity to activity over time. A flow diagram shows the movement of materials from one place to another. And in this case, we're showing the carbon cycle in a loop here. The same situation can be modeled in a causal loop diagram where we're looking at causes and effects. So increasing plant mass over time has an effect of increasing atmospheric oxygen. So flow tends to represent time. I've contrasted the two diagrams here, the flow diagram and the causal loop diagram, and you can dwell on that at your leisure. Another point to make is that we have singular causes. The arrows represent singular causes, but also composite. So increasing road miles cycled per person is a composite cause of 3 singular causes. And there is at the other end, there's a composite effect of 3 singular causal flows are having a composite effect in a given time span on the target. So build up our meta model of causality. To begin, the stock level over time has many state changes, and each state change relates to one stock level. So that's a one-to-many relationship. Here we have a causal flow has one cause and one effect. Generally, when you have one-to-one, you can show one thing as an attribute to the other. Here we're saying the causal flow has an attribute of being a feature that is a singular cause and a singular effect. What about relating the stock to the flow? Well, we had a model earlier, which is a kind of general pattern for relating such concepts. And you can use the same pattern here for an entity relationship diagram and the same pattern for a stock and flow diagram. Every flow has a cause end and an effect end. And every stock can have any number of causal flows attached to it. It's a little bit more complicated than that to allow for cause-only flows and target-only flows. We can say that a state change may be a multiple cause, which is composed of one or more singular causes, and it may be a composite effect of one or more singular effects. If we add all that together, we get the diagram I started with, the meta model of causality and causal loop diagrams. Can we generalize that from to all kinds of causality? Well, I've had a go at that, and that's where we're going to finish with this diagram. It's a suggestion, no more than that, for a model of all kinds of causality.